A massive explosion rips through a chemical plant in Pasadena, Texas. The blast is so powerful, it registers as a 3.5 magnitude earthquake. Windows shatter 8 miles away in downtown Houston. Inside the Phillips 66 complex, steel structures twist, buildings collapse, and a giant fireball rises over the Houston Ship Channel. In seconds, the refinery turns into a burning disaster zone. When it's over, 23 workers are dead, 130 more are injured, but the explosion didn't come out of nowhere. Just 2 minutes earlier, workers in Reactor Unit 6 heard something unusual. A hiss. Not the normal sounds of the plant. A pipe had ruptured, releasing 85,000 pounds of flammable hydrocarbons into the air. Ethylene and isobutane forming a massive invisible vapor cloud drifting through the unit. Workers began to run, because once a cloud like that forms inside a refinery, it only needs one thing, a spark. And on October 23rd, 1989, it found one. The Phillips 66 Houston Chemical Complex wasn't a small operation. Since 1956, this sprawling facility along the Buffalo Bayou had been producing high-density polyethylene, HDPE, the plastic that makes everything from milk jugs to shopping bags to children's toys. The complex had a massive output, 1.5 billion pounds of HDPE per year. That's roughly 15 to 20% of the entire United States supply. On any given shift, over 1,100 people worked on site. Phillips 66 employed about 900 permanent staff. Another 600 or so were contract workers, maintenance crews, construction teams, specialists brought in for specific jobs. The plant operated around the clock, multiple reactor units running simultaneously, each one a pressurized chemical factory producing millions of pounds of plastic. By all outward appearances, it was a modern facility. Safety procedures documented, training programs in place, regular inspections. At least, that's what the paperwork said. But in the Houston Industrial Corridor, there was already tension brewing. The Oil, Chemical and Atomic Workers Union had been raising concerns for months. Complaints about unsafe practices by subcontractors, lapses in maintenance protocols, shortcuts that saved time but added risk. The warnings were filed, meetings were held. Nothing changed. And then, on August 1989, just 2 months before the disaster, something happened that should have been a wake-up call. Subcontractors opened a piping line without properly isolating it first. Flammable solvents vented. The vapor ignited. 4 workers were burned. 2 of them died. OSHA cited Phillips for improper lockout procedures. The fine was minimal. The incident was reviewed, documented, filed away. Operations continued as normal. On October 21st, 1989, a Sunday, another maintenance crew arrived at Reactor 6. They had a job to do, clear polymer blockages from the settling legs, just routine work. To understand what went wrong, you need to understand what these reactors actually do. High-density polyethylene starts as ethylene gas. Inside a loop reactor, 150 feet of pipe circulating like a pressurized racetrack. The ethylene dissolves into isobutane solvent, along with hydrogen and hexene. The mixture is heated to 230 degrees Fahrenheit and pressurized to 600 pounds per square inch. Under those conditions, the ethylene molecules link together. Polymerization. They form long chains that become solid plastic. But sometimes, chunks of plastic solidify and settle. They collect in vertical side pipes called settling legs, designed to catch the polymer before it clogs the main loop. Every few weeks, these legs fill up with hardened plastic plugs. These blockages have to be removed or the reactor can't function. Clearing a settling leg is routine maintenance, but it's dangerous work. You're dealing with a pressurized system full of flammable chemicals at temperatures and pressures that turn mistakes into disasters. One valve opened when it shouldn't be, and all that pressurized hydrocarbon finds the outside air. When that happens, it becomes a weapon. The Fish Engineering crew arrived on Sunday, October 21st. Fish Engineering was a contractor company. They'd been hired to handle the maintenance work on Reactor 6's settling legs. The polymer blockage in the second settling leg was stubborn. It needed attention. The crew began their preparation, reviewing procedures, setting up equipment, getting ready for the actual clearing work that would happen Monday. One Phillips operator later recalled something about that contractor crew. Chuck Soules said they seemed uncertain. His exact words, "The contractors did not know what was going on during the procedure." That uncertainty should have raised flags. But the work continued. By Monday morning, October 23rd, everything was set up. The crew was ready to clear the blockage. The procedure required isolating the settling leg from the pressurized reactor. You can't safely work on a piece of equipment that's connected to 600 psi of flammable chemicals. The isolation has to be absolute, physical, verifiable. Though the standard way to do this: install a blind flange, a solid steel plate bolted directly onto the pipe. No moving parts, no valves that could fail. A physical barrier that makes it impossible for pressurized gas to reach the work area, or depressurize the reactor entirely. Drain the system. Confirm zero pressure. Create conditions where a mistake can't become a catastrophe. But that's not what happened on October 23rd. Instead, the crew used what Phillips called an alternative isolation method. They relied on a closed valve. They trusted an indicator showing no flow. They assumed the system was safe to work on. They were wrong. The fatal pivot. Shortly after 1 p.m. on October 23rd, the crew made a decision that would kill 23 people. A safety blocking device was removed from the valve system, and the crew needed to connect pneumatic hoses, the airlines that control whether the large ball valve stays closed or opens. There were 2 hoses, one for air supply, one for discharge. They looked identical, same size, same fittings, same color, interchangeable. The crew connected them, but somewhere in that process, maybe rushed, maybe distracted, maybe just unlucky, the hoses were reversed. Air supply where discharge should be, discharge where supply should be, with the hoses backward. And the valve's control system read the opposite of reality. The 10-inch ball valve, a Demco brand valve that was supposed to remain sealed, began to open. No alarm sounded. The indicator still showed closed. Everything looked normal. But inside the pipe, the valve was rotating, opening, creating a path. The reactor was running, pressurized to 600 pounds per square inch, full of flammable hydrocarbons at 230 degrees Fahrenheit. And now it had a direct opening to the atmosphere. The reactor began emptying itself into the yard. Release. 2 minutes to catastrophe. The hiss started immediately. Not loud at first, just wrong. A sound that didn't belong. Then it became a roar. Workers near the polyethylene unit heard it first. A deafening rush of escaping gas. Then they saw it. White vapor pouring from the open pipe, billowing up and spreading through the scaffolding and equipment like a living thing. About 85,000 pounds of process gas released in seconds. Ethylene, isobutane, hydrogen, hexene. A massive cloud of flammable vapor expanding through the plant, flowing along the ground, searching. The alarm siren sounded across the complex. Workers ran. Mike Sinai was 23 years old, a contract worker in the area. He later described what he saw. "I saw white gas in the air. We heard the alarm. People were falling into ditches. Men sprinted for exits, dove behind equipment, jumped fences. Some didn't know which direction to run. The cloud was everywhere. The vapor kept spreading. Heavier than air, it flowed like water through the unit, around corners, between buildings. An invisible wave searching for any source of ignition. A hot pipe, an electrical spark, a running motor, anything. Somewhere in that expanding cloud, it found one. 90 seconds, maybe 2 minutes. That's all the time between the first hiss and what happened next. At 1:05 p.m., the vapor ignited. The explosion was instantaneous and overwhelming. 2.4 tons of TNT equivalent. The blast obliterated everything within 250 feet of Reactor 6. A blinding flash. A thunderous boom that echoed across the Houston ship channel. Mike Sinai. "Metal was flying in the air and it's just blowing up. It knocked me about 30 feet and you just got up and started running. I jumped the fence and ran over the bayou and just kept on running. The fireball rose hundreds of feet into the air and black smoke followed. Steel structures, multi-story pipe racks, reactor frameworks, bent and twisted like tinker toys. The control room for the polyethylene unit, located too close to the process equipment, was completely destroyed in the first blast. 8 miles away in downtown Houston, windows shattered. Shirley Morales lived about a mile from the plant. The blast knocked things off my walls and blew my windows and screens out. And I thought a bomb had hit my house, until she ran outside and saw the columns of flame and smoke. Mike Buchanan was driving on Interstate 10, 5 miles away. Everything shook with that tremendous boom, and then it began raining pieces of sheet metal. Seismographs registered it as a 3.5 to 4.0 magnitude earthquake. But the nightmare was just beginning. The secondary explosions. 10 to 15 minutes after the initial blast, as workers fled and first responders rushed toward the plant, a second massive explosion rocked the complex. Two 20,000-gallon isobutane storage tanks had been sitting near the polyethylene unit. The spreading fire reached them. The tanks ruptured. Another enormous fireball erupted into the sky. Workers and firefighters dove for cover as debris rained down again. 25 to 45 minutes after the first explosion, a third major blast occurred. Then another polyethylene reactor vessel in an adjacent unit failed catastrophically. The heat and pressure from the surrounding inferno breached its containment. Over the next hour or two, witnesses counted up to 10 separate explosions, equipment failing, pipelines rupturing, chemical storage areas succumbing to the fire. Each new explosion sent fresh waves of smoke and flame across the complex. The facility had become a war zone. Black smoke was visible 15 miles away. The emergency sirens wailed. Mutual aid alarms rang out across Pasadena, and the fires kept burning. The Phillips 66 Internal Fire Brigade responded immediately. Despite the chaos, despite losing colleagues in the blast, these trained employee responders began fighting the flames with whatever equipment they could reach. Within minutes, the Channel Industries Mutual Aid Network activated. Fire departments from Pasadena and neighboring jurisdictions converged on the scene. The U.S. Coast Guard dispatched firefighting boats. Specialized crews from other industrial facilities arrived with foam trucks and equipment. The Houston Ship Channel was closed to traffic. The FAA restricted air traffic overhead. But fighting this fire was nearly impossible. The initial explosions had wrecked the site's infrastructure, and critically, they had destroyed the firefighting water system. The complex didn't have a separate firewater supply. It relied on the same water lines used in chemical processes. The explosions severed these lines. Fire hydrants were sheared off at ground level. Water pressure, exactly when it was needed most, plummeted to nothing. Backup diesel pumps that could pressurize the system failed. One had been out of service for maintenance. Another ran out of fuel after running briefly. Electrical fire pumps went offline when their power cables burned through. Firefighters had to improvise. They laid hose lines to retention ponds, to the cooling tower basin, to the water treatment facility on site, to a neighboring company's water main. Anywhere they could get water, they used specialty foam pump trucks from mutual aid partners, mass deluge equipment, anything that could throw water and foam onto the flames. It was a 10-hour battle. Crews poured thousands of gallons onto the twisted wreckage of the plant. Slowly, gradually, they gained ground. The main fire was brought under control late that night, but even then, smaller fires and hot spots continued to smolder. The water rescue. During the height of the fire, over 100 employees found themselves trapped. The administration building sat on the complex's waterfront, along the Houston Ship Channel. Normal exit routes had been cut off by flames. Workers couldn't evacuate on foot without walking through the inferno. They took shelter in the building and waited. The Coast Guard and Houston Fire Department mobilized boats. Firefighting vessels and rescue craft crossed the ship channel to the plant's dock area. One by one, they ferried more than 100 people to safety on the opposite shore. The water evacuation likely saved many lives. Those employees would have had no way out otherwise. The heat was too intense to enter the worst-hit areas until the next morning, October 24th, even after the flames were extinguished. The wreckage was structurally unstable, twisted metal, collapsed structures, the risk of further collapse. Search and rescue teams waited for the site to cool. Then they moved in carefully, documenting everything, searching for victims. The Harris County Medical Examiner's Office coordinated the recovery. They worked methodically. Any physical evidence that might explain what happened had to be preserved. The grim count was confirmed. 22 workers dead at the scene. One more would die later from injuries. 23 total. Most of the bodies were found within 250 feet of Reactor 6. 15 of them were within 150 feet. They had been at ground zero when 2.4 tons of TNT equivalent detonated. Most didn't have time to understand what was happening. Another 130 people were injured badly enough to require hospital treatment. Many were airlifted by helicopter on the afternoon of the 23rd. Burns, trauma, blast injuries, as over 300 individuals in and around the plant sustained some degree of injury from the explosions and debris. But now the question everyone was asking could finally be investigated. How did this happen? OSHA arrived within an hour of the initial explosion. Inspectors and safety specialists moved in quickly to preserve evidence. They documented the scene, photographed debris, collected samples, interviewed survivors. Over the next 6 months, OSHA engineers reconstructed what happened with forensic precision. They traced the sequence step by step, the maintenance procedure, the isolation method, the valve operation, the hose connections, and they found the answer everyone had been asking. The crew working on the settling leg had no effective isolation between the pressurized reactor and the section they were working on. They used Phillips' alternative isolation method, trusting a closed valve and the absence of flow. But that method failed. The pneumatic hoses controlling the valve had been connected in reverse. When the crew thought they were keeping the valve closed, they were actually commanding it to open. The 10-inch ball valve opened directly to atmosphere. 99% of the reactor's contents explosively decompressed in seconds. 600 psi of pressure forcing 85,000 pounds of flammable chemicals into the open air. Then investigators found something even worse. A critical design flaw that made this disaster inevitable. The air supply hose and the discharge hose for the valve were identical. Same diameter, same threads, same fittings, same appearance. No labels, no color coding, no physical difference whatsoever. An operator could reverse them, and no one would know until it was too late. Even the valve position indicator could show closed when the valve was actually open. Human error made possible, made likely, by catastrophic design. But the investigation didn't stop there. The procedure that killed OSHA's conclusion was damning. The procedure for clearing settling legs was grossly inadequate. It didn't ensure proper lockout. It didn't require physical isolation. It left too much room for human error, and Phillips knew it. Internal documents, uncovered during the investigation, showed that the company's own engineers had noted issues with this procedure before. They had recommended improvements, and management ignored those recommendations. The plant layout made it worse. OSHA found inadequate separation between buildings and between occupied work areas and hazardous equipment. Distances violated accepted engineering practices. The control room was so close to Reactor 6 that it was demolished in the initial blast, which meant no emergency shutdown actions could be taken. The isobutane storage tanks were close enough to the process unit that the fire caused secondary explosions, so there were no blast walls, no segregated zones, no protection for escape routes. The firewater system had no dedicated supply, a known vulnerability, and the heavy reliance on contractors for critical maintenance without sufficient oversight created what investigators called diffused responsibility for safety. The fish engineering crew was performing a high-risk task at the heart of the operation. No, but they weren't as experienced or trained in the plant's hazards as they should have been. Chuck Soul's observation that they did not know what was going on was prophetic. The receipts. After 6 months of investigation, OSHA presented its findings. 566 willful safety violations, 9 serious violations, all attributed to Phillips' 66 company in connection with the explosion. Fish Engineering, the contractor, received 181 willful violations and 12 serious violations. And OSHA proposed a record-setting $5.7 million fine for Phillips, another $730,000 for the contractor. At the time, these were the largest penalties OSHA had ever sought. U.S. Secretary of Labor Elizabeth Dole made a statement that cut through any remaining ambiguity. This tragedy is magnified by clear evidence that this explosion was avoidable. He had recognized safety procedures been followed. She noted that OSHA found clear lapses where corrective actions were called for but largely ignored by the company prior to the accident. OSHA's official report to the president listed the underlying causes: poor risk assessment and management, lack of redundant systems and fail-safe engineering, inadequate maintenance of equipment, poorly conceived operational and maintenance procedures, incomplete employee training. Every single factor either led to the accident or made its consequences worse. And then there was the August incident, 2 months before the big explosion, the accident that killed 2 workers when contractors opened a line without proper isolation. OSHA had cited Phillips for improper lockout procedures. The warning was documented. Nothing changed. Phillips Petroleum initially contested the citations. So did Fish Engineering. A legal battle loomed. But in 1991, a settlement was reached. OSHA agreed to drop the willful designation from the violations. In exchange, Phillips paid a $4 million fine and committed to implement extensive process safety management reforms at the Pasadena complex and other facilities. Phillips also settled numerous lawsuits with victims' families confidentially. Workers' compensation claims were paid to the injured. Internally, the company overhauled procedures, stricter permit systems for maintenance, improved contractor training, new emergency response protocols. But the question remained, would it actually change anything? The Phillips Pasadena explosion became a catalyst for change in the petrochemical industry. In 1992, OSHA finalized the Process Safety Management Standard, a comprehensive set of regulations designed to prevent major chemical accidents. Companies had to identify hazards, maintain equipment properly, train operators thoroughly, manage changes safely, plan for emergencies. The PSM standard became law. Phillips Pasadena was cited during the rulemaking as an example of why these regulations were urgently needed. Across the industry, companies re-examined how they used contract labor, greater emphasis on training, better oversight, clear responsibility for safety in multi-employer work sites. Engineering practices evolved. New plants were built with better equipment spacing, fortified control rooms, automated isolation valves, redundant safeguards, fire protection systems improved, dedicated firewater reservoirs, looped hydrant systems. The lessons seemed learned, but here's the bitter truth. The Phillips Pasadena complex was rebuilt, and it continued operating through the 1990s. In 1999, there was another explosion at the same plant. 2 contractors burned to death. In 2000, another fatal explosion. Worker safety, despite all the regulations and reforms and promises, seemed to have remained just a dead letter. Close October 23, 1989, started as a routine maintenance day. A contractor crew working on Reactor 6, standard procedure to clear a polymer blockage from a settling leg, then a hiss, and a white cloud spreading through the unit. 2 minutes later, 2.4 tons of TNT equivalent detonated. 23 people were gone. The explosion wasn't an accident. It was the culmination of every warning ignored, every shortcut taken, every safety measure dismissed as too expensive or too inconvenient. 566 willful violations found by OSHA. Internal documents showing engineers flagged the dangerous procedure. Management did nothing. A fatal accident 2 months earlier with the same root cause. Nothing changed. A contractor crew that didn't fully understand the system they were working on sent in anyway. An alternative isolation method that wasn't isolation at all. Identical hoses that could be reversed with no warning. A control room placed so close to the hazard that when disaster struck, no one could shut anything down. A water system designed to fail at the worst possible moment. The explosion wasn't the first failure that day. It was just the loudest, the one no one could ignore anymore. Now drop your thoughts about this in the comments below. Like and share this video with anyone who works in industrial safety. And don't forget to check out the other videos on our channel.